Okay, here we go. I'm now going to share my screen. Move this around. Okay, so as I mentioned, I'll first cover a very simplified primer on choropleth mapping in using GeoPandas. What are we going to use? Primarily GeoPandas and then Matplotlib and libPySAL just to pull the sample data out. We're going to be using the police data set for this one because it doesn't have as many observations as the Chicago one. So here are the imports. It's the same as what we did last week. So we import GeoPandas as GPD. We import that's a new one, Matplotlib PyPlot as PLT, and then libPySAL from libPySAL examples, we import getPath. What this means is that we only have to write getPath. We no longer have to write libPySAL.examples.getPath. So it's just a simplified notation, and I'm going to run this. So we're going to run it live in the notebook, Jupyter notebook. I thought the Jupyter notebook looked a little better on the screen than the visual code, but if you think otherwise, let me know and I can switch. It doesn't matter which one I do, but I just looked at it and I thought this one looked a little clearer than the white on black in the visual code. So we're going to use the same as last week, read file, and a new one is plot. From libPySAL, we do getPath, and this is optional, but if you want to save your figures as PNG files, for example, to put in a paper or something like that, that's save fig. So the files, again, same setup as before. We set it all up on top. If you want to run this for a different data set, you just change this to another data set, but make sure you have loaded it as an example beforehand. Otherwise, it'll give you an error message. So see, this is what I mentioned. We just do in path is get path, no longer the full expression, and then we read the GeoPandas data frame. So now we have a GeoPandas data frame. I won't, if you want to check it out, you do info or you print the columns if you want to know what it is. So we're going to start by making a really ugly thing. This is the default map in GeoPandas. So I'm not doing anything fancy. I just say, this is the GeoPandas data frame. I apply the plot method to that data frame. I pick the column, which is per capita police expenditures in Mississippi. And then I set legend equal true. If you don't set that, you still get a map, but you don't get a legend. Okay, so we do control return, and this is our first map. Okay, if you do this in a cartography class, you will fail. Okay, for a number of reasons. One, there's this ugly axis thing. There's these numbers on the side, and a continuous color shading is usually not recommended for a choropleth map because even though we think we may be able to see continuous gradations, we can't. Some people are better at this than others, but we typically can only see a handful of different shades. And so you're really kidding yourself putting a continuous color map for a map. So we will step away from that very quickly. So we're going to use some explicit functionality from Matplotlib. And I found personally that it takes a while to get the logic of Matplotlib. If you've worked with it before, then it sort of is a natural, and you very quickly start assuming that it is a natural, but I still don't quite find it a natural, but is this weird thing where you set something up and you call it a figure and an ax. And the figure is just how you arrange things on the page. You have one figure or you have multiples, two rows with two figures or three columns with two figures, all that stuff you set up in figure. We won't be doing that, so I won't be talking about it. But if you want to do fancy stuff, by all means, look it up. There's a lot of documentation out there. The ax is really the figure that we draw. And so that is an object. And once you set up that object, you can add layers, all kinds of graphical layers to it. And then you can set all kinds of options, like giving it a title and getting rid of the box and things like that, okay? But these all pertain to ax as an object. So if you're not familiar with this, think of what I just did with DFS. I read this shapefile and turned it into a GeoPandas data frame. At this point, we're inside Python. It's no longer a shapefile. It's a GeoPandas data frame. And we apply the plot method to that data frame. So in very much the same way, we're going to set up an ax object and then start applying different methods to that object. So the initial step says this is going to be a plot applied, oops, sorry, I don't know where that came from, applied to our GeoData frame. This is the variable that we will plot. This is the legend. This is exactly the same as what we had before. And the reason I show you, and you probably already know this, in Python, there's usually several different ways of doing the same thing, of obtaining the same result. And if you're not used to that, it can be very confusing because you see something, you say, why are they doing it this way? Well, it's exactly the same. What I did before was a shortcut. I skipped the ax part because I was only doing one thing. I didn't really need the ax thing. But once you start doing more than one thing, making a map, getting rid of the box, putting in a title, setting a legend in a particular space, then it's worth using the ax object and just tacking on new things as you build the graph. And that's the nice thing about Matplotlib. It's incredibly powerful. You can make the most complex graphics by just adding layer and layer and changing the characteristics of the layer, like, you know, how transparent is it? What color does it have? How thick are the lines? All this kind of stuff can be manipulated. So you can spend a whole semester, a quarter, doing this stuff. I just want you to see the basics, get a little bit of a sense of how it works. If you don't get a sense, just use it as a template. Copy and paste, change the name of the variable, and you have a map, okay? So we're setting this up, and then we apply another method to this object. So here's our graphic, and we say, turn off the axis, get rid of the box around the map. So if we run this, why am I not doing this? What happened? Okay, here we go. So I still have my ugly colors, but no more box, and we can proceed. Now, as I said, you can do the same thing. It's a matter of taste. Like, I prefer to spell out everything I do on a separate line. Some people like to cram all the commands in one single line, and you can. You can chain these things. Now, the reason I prefer to put it on separate lines is with the chaining, you have to be careful because sometimes the logic of the chaining doesn't work exactly the way you think it's going to work. So if you put it on separate lines, you're always in control. That's just me. So if we do this, again, we get the same. Okay. So enough of this bad map. We're going to focus on some map design characteristics. This is not a cartography class, and each of the, I mean, you can spend months talking about this. The basics are you need a classification. So we are dealing with continuous variables. We show them as a choropleth map. Choro comes from choros, which is region in Greek. So it's a map for regions. It's also called a thematic map because it maps a theme, a variable. So what you do is make a graphic of a spatial representation of a histogram. Now you're all familiar with a histogram for a distribution. You have a continuous distribution, you put the observations in bins in increasing order. A map is the same thing. You have to put the continuous variable into bins following a particular classification. And maybe more so than with histograms, where you may not think about it too much, the type of classification matters. And I'm going to go over 5 basic types. 3 are classic cartography types. 2 are what I call statistical maps, in that they provide a little more information about special characteristics of the distribution, particularly outliers. So classification is the first characteristic. Second one is color. Color is very important. There's a whole science behind using color schemes for graphics and for maps. There's a really useful website out there. It's called Color Brewer. It's by Cindy Brewer. And what is really useful for it, and you don't always think about this, is that the colors look differently on your screen, in a projector, and printed on paper. And so it wouldn't be the first time that somebody makes a presentation and the map looks great on their screen, but it's all blue or all green on the projector. So Color Brew is great because it has different schemes for these different media. So if you need something that looks good on paper, you may not use the same color scheme as for something that you want to look at on your screen or project. So we'll talk a little bit about color schemes, and then we'll talk about the legend, which is directly tied to the classification. So the classification in the way this is done in GeoPandas is under the hood. It uses another package from PySAL, which is called Matplotlib. So Matplotlib is a package that implements multiple classifications for maps. The ones we will use are called, they're specified in an attribute called scheme, argument scheme. And the common ones are quantiles. That's a quantile map. A quantile map is exactly what it says it is. So you look at the quantiles of a distribution. The most common ones are quartiles for 4. So you have 25%, 50%, 75, and 100, or quintiles for 5. 6 categories are used too. The one good thing about quantile maps is that the range, the number of variables in each category is the same. So in a quartile map, you have 25% of the observations in the first category, the next 25 in the second category. And so if you have 40 observations, each category has exactly 10 observations in a quartile map. However, the range is not constant. So you could have situations where 10 observations have very similar values, so the range is very narrow, and then in the next quartile, the range is very large. So the good thing about a quantile map is same number of observations in each group, The bad thing is you don't control the range. And so the scheme argument for a quantile map is quantiles. A second type of map is equal interval, and the scheme name is equal interval, one word. That's the opposite. There you control the range. That's what's called equal interval, the same interval for each category, but you don't control how many observations in each category. So it could be, depending on the shape of the distribution, that you end up with very many or very few observations in a particular range, depending on the distribution. A third one uses an algorithm. It's called natural breaks, which breaks the distribution in some optimal sense. If you're familiar with clustering, k-means, I know several of you are familiar with k-means. This is like k-means in one dimension. So you have one variable and you tell natural breaks, find me the cut points that yield the categories that are most similar internally and most dissimilar between them. So this is kind of a algorithmic break point search. But again, you get nice breaks, but you get no guarantee either about the range or about the number of observations. So quantile maps, you control the number of observations. Equal interval, you control the range. Natural breaks, you don't control either one of them. Okay. And then there's two statistical, what I call statistical maps. In map classify, they're called STD mean, standard mean, which is a standard deviational map. So here in the other maps, you pick the number of bins, which is K as the attribute. So if you want a quartile map, you set K to 4. In the statistical maps, you don't choose the number of bins, they're chosen for you. The cut points are based on statistical criteria. In a standard deviational map, the cut points are standard deviational units. So if you think of standardizing your variable, making sure the mean is 0 and the variance becomes 1, then every unit is 1 standard deviation. So by convention, we take observations that are more than 2 standard deviations from the mean as being outliers. You don't have to go with 2, you can go with 3, but those are far away from the mean. And so then the question is, are they part of the same distribution or not? And really, what we're concerned with is what is called thick tails. Are there more extreme observations than you would expect? And then we have something funky going on about the distribution. The difference between looking at that with a distribution or a QQ plot or something like that is that here we know where they are because it's a map, right? And then the box plot, which is really a box map, is the spatial representation of a box plot. So again, it gives you the quartiles, but in addition, for the lowest quartile and the highest quartile, it gives you the observations that are outside the hinge. So the hinge is either 1.5 times the interquartile range or 3 times the interquartile range. So again, observations that are outside of that, especially if they're quote unquote too many, are looked at with suspicion. And again, we know where they are on the map. So there's a couple of options that we can manipulate. The default hinge for a box map is 1.5. If you want to change that to 3, it's a little tricky and it's not obvious in the documentation, but you use this classification underline keywords dictionary. It's a dictionary. So every item has a keyword. For example, hinge, of course, this is what I'm telling you. You have to know this. If you don't know this, you're stuck, right? So you have to know that you have to set the hinge keyword for the classification keywords dictionary to 3, for example. And similarly, for the standard deviational map, the default setup is that one standard deviation above and below the mean are in the same category. If you want to show the mean as a cut point, that's an option that you set by specifying anchor to true. Again, in the same way. So classification keywords, then you would have anchor in quotes, a colon equal and not equal, colon true. Okay, if you want to know more about it, by all means, check out this documentation. This one, I don't want to say too much about it. It's incredibly powerful. You can put the legends just about anywhere you want. You can manipulate the location, how far it is from the map, whether it has a title or not. Those things are very technical, but basically you can do anything you want. Just look it up in the documentation. I just use this one as kind of my standard go-to, and it works for most of the examples that we have. So let's just go through a couple of examples, and we're going to start with a simple quantiles map. And so look at what I'm doing here. I start by setting up the Ax object, right? And that's a plot applied to GeoPandas data frame. The variable is called column, is police. The scheme is the classification, is called quantiles. K is the number of bins. We set it to 6. We want a legend, true. And then this legend keywords thing. Look at the thing here. The title keyword is set to the name of the variable. You can make this generic. I'll show you an example in a few minutes. Then we set the set title property of the X object to quantiles, and we turn the box off. So now we still have something that looks a little weird, but it has a title, it has a legend, it has a color scheme. Each of these has 1/6 of the observations in them, but look at how different the range is. For example, the lowest range goes from 49 to 249, the highest range from 1275 to 10,975. Okay. So there's 3 maps for which we have to set K. And rather than typing this 3 times, I'm going to run this as a little loop. And here we have the 3 types of schemes. It picks up the scheme as I. So for I in this list, I just replace I by the value, and it will make 3 maps.
Add the units for the place.
The units for what? Oh, these are all set. I mean, you can set the point size. Is that what you mean?
What is the unit for?
Oh, I mean, for each variable that is set in GeoPandas data frame. So that is something you can put that in the title if you want. This police one is police expenditures per capita for counties in Mississippi. Is that what you mean? Well, you need to know what the variable is. That has nothing to do with the map. Okay. But we will talk about this. Well, I will talk about it, that you have to avoid making maps of what is called spatially extensive variables. So totals, total number of people, total number of houses. This is not total police expenditures. It's police expenditures per person. So the size of the county is taken out of the equation by dividing it by a common denominator. So here we have equal intervals. The intervals are the same. but just about everything is in this first category. So that doesn't really help us much in this particular example, right? And then natural breaks is a little better, a little more nuanced, but still there's a lot of observations in the lowest category, right? So each of these classification schemes gives you a different perspective on the spatial distribution of the data. And so knowing that and being sensitive to that is important, because one size does not fit all, right? For some distributions, a quantile map is perfect. For others, it's terrible, right? And we'll see an example, I think, of a bad one a little bit later on. So then these kind of maps, as I mentioned, they don't need K, because K is predetermined by either the standard deviations or the quartiles for the box map. So here's the standard mean map, where the mean category plus or one standard deviation from the mean basically takes over everything. Most of the observations are in that narrow band, and then there's a few counties with much higher expenditures. Okay. I forgot which is which, but one of them is Jackson, Mississippi, which is the state capital and which has more police expenditures. Box plot is very similar, 6 categories. Look at this at this map carefully. Can you find observations in this darkest category? No. Why not? It's a negative number. And this is Tobler's rule. Look at the distribution of the data. If it has negative numbers for per capita police expenditures, I don't think that happens, right? So there are no observations in these categories. And because we don't control it, right, this is built in. It looks at the quartiles and it takes the first quartile. I mean, in this case, these two are the first quartile. So the first quartile goes to 291. But no observations are in the outlier, in the lower outlier, and all observations are positive. So a lot of this category, they're all the same width. A lot of this category has nothing in it, okay? So, what is this? So this is an illustration of the setting the option of the criterion of an outlier. So the default is 1.5. And if you set it to 3, you have to do it this way. This is a little different from the way you do it in Matplotlib. When they first used this, I couldn't get it to work. And then I figured out you have to pass it through this dictionary, not directly as in Matplotlib. So this has even fewer outliers than before. Standard deviational map with the midpoint shown. A little bit better, but still most of the observations are around the mean. So one thing that is not good about this is the color map. What we want is we want to control that. And in Matplotlib, there is a large number of pre-built-in color maps. They are set by the argument CMap. So CMap picks a particular color sequence. And there's 2 types that we're interested in. One is a sequential one, where you go from low to high, so to speak, or from cold to hot. And so there's different color schemes that follow that. We'll show blues and yellow, orange, red. So yellow orange a little bit warmer, red a little bit warmer. And then we have another type of color schemes where the interest is called a diverging legend, where you have the middle and then the colors go away from the middle, typically in different types of colors. So you would go below the middle in blue and above the middle in red or some other scheme. So these are diverging color schemes. They are good for box maps and for standard deviational maps. They're not good for quantile maps or equal interval, which are sequential classifications. So you want a color scheme that goes from cold to warm, right? So let me just show some of these colors, and then you pick the ones that you like the best. This is the blues one. So everything here is the same. That's why I said, you know, if you're not totally comfortable with this, just copy and paste and change what you want to change. So you change the variable, or you change the scheme, or you change the color map, but you just keep everything else as it is. So these are the blues from light blue to dark blue. And you see the gradation much better in this classification scheme than in the default that we just were using. This one is the one I use the most often, is from yellow going to dark brown. Again, same thing, you know, you see the low values are light colored, the higher values are darker and darker, the highest values are the dark brown ones. Then this is a diverging scheme. It's a box plot, and it's called seismic. So you see it's going this way for the low values, red way for the high values. And the outliers are in dark brown, so they pop out immediately. Okay. And then a gotcha. So copy and paste. I'm going to do standard mean. I'm going to use this brown, white, red, blue, white, red scheme. And everything else is the same. Where did the Mississippi go? Right. What is missing? Borderlines. There's no borderlines. Now, we didn't notice it because our eyes are faking us out, right? We look at this map and somehow we think there are borderlines. We make them up in our mind. They're not there. And then, of course, when you do this, you see that they're not there. So then to make sure there are borderlines, we set edge color black, and you can specify a line width as well. And now we're in business. So you have everything. There's lines, you see all the counties, and you see the colors. You can save the map to a file. That is this save fig. I won't do it, but one thing, you specify the name of the file, and then it's the default is 300 DPI, which for most journal articles is not enough. So if you ever want to use this map in a publication, set the DPI to 600 or even more. I mean, you could set it to more, but then it takes longer.
Say that diversion is good for box and standard mean, but sequential for other.
Because box and standard mean are not about ordering, they're about moving away from a center point. And the other ones are going from low to high. So then, yeah, you can also just, in case you wanted to do this, oh, I just saved it. If you just want nothing, then you have the boundaries. So notice I didn't set a column. So there's no variable, but there's still a shape. There's still lines, everything is still there. Okay, so this is everything you ever wanted to know about maps in a half hour. Right. That should be good enough for our purposes.